Hello guys, I'm really glad to see you back again. Do you guys remember when we started using definite integrals and then we started applying this concept for getting the area under a curve in a given interval a, b? But what if a and b are not finite, meaning that we compute the area under a curve from minus infinity to a finite value, or from a finite value to positive infinity, or even doing the integral from minus infinity to infinity of a given function? Well, that's exactly what we're going to do today, because we're going to deal with the concept of improper integrals. As I mentioned in the introduction, we want to compute the area under a curve of a function in an interval where one of the extremes is not finite or both of them are infinite. For example, if we want to compute the area under a curve of a function in an interval from minus infinity to a point b, we will need to do the integral from minus infinity to b of f of x dx. And for doing that, we will need to do the limit when t goes to minus infinity of the integral from t to b of f of x dx. Now, let us try to compute the area under the curve of the function f of x equal 1 over 1 plus x squared in the interval from minus infinity to 0. For doing so, we need to build our improper integral, meaning the integral from minus infinity to 0 of dx over 1 plus x squared. For solving this integral, we need to take the limit when t goes to minus infinity of the integral from t to 0 of dx over 1 plus x squared. Now, the result of this integral is equal to arctangent of x, which we need to evaluate from t to 0. And by using the first fundamental theorem of calculus, this is equal to arctangent of 0 minus arctangent of t. But remember that we need to take the limit when t goes to minus infinity. Now, arctangent of 0 is 0. And when t goes to minus infinity, arctangent goes to minus pi over 2. Therefore, our result will be equal to pi over 2. And the interpretation that we need to take from this is that the area under the curve of the function f of x equal 1 over 1 plus x squared from minus infinity to 0 is equal to pi over 2. Now, let us consider another case in which we want to know the area under the curve of a function f in an interval from a finite value a to infinity. For doing so, we need to compute the integral from a to infinity of f of x dx. But we know that we need to take the limit when t goes to infinity of the integral from a to t of f of x dx. And that will be the way to compute the area under a curve in an interval from a to infinity. Let us consider the following example. Let us try to get the area under the curve of the function f of x equal e to the minus x from x equal 1 to infinity. Now, we know that we need to take the integral from 1 to infinity of e to the minus x dx. And as well, we need to take the limit when t goes to infinity of the integral from 1 to t of e to the minus x dx. We solve the integral and we get as a result minus e to the minus x, which we need to evaluate from 1 to t. And we get minus e to the minus t plus e to the minus 1. Now, we need to remember that we have to take the limit when t goes to infinity Now, if t goes to infinity, minus e to the minus t goes to 0. Thus, we end up having only e to the minus 1, which can be rewritten as 1 over e. And that will represent the area under the curve of the function f of x from 1 to infinity. Now, not all improper integrals have a finite value when we deal with the limit. If the limit does not exist, then we say that the improper integral diverges. For example, if we take the integral from 1 to infinity of the function 1 over x dx, then we know that the integral of 1 over x dx is equal to ln of x. And if we apply the substitution, we will get ln of infinity minus ln of 1. ln of 1 is equal to 0, so no problem there, but ln of infinity is equal to infinity. Therefore, this improper integral diverges. Now, the last case involving improper integrals is the case in which we want to compute the area under a curve of a function f of x from minus infinity to infinity. For doing so, we are going to do the improper integral from minus infinity to a finite value c, and then from that finite value c to infinity, meaning that the integral from minus infinity to infinity of f of x dx will be splitted as the integral from minus infinity to c of f of x dx plus the integral from c to infinity of f of x dx. For example, let us try to find the area under the curve of the function f of x equal 1 over 1 plus x squared from minus infinity to infinity. The way that we will do that is by solving the improper integral from minus infinity to 0 of f of x dx plus the integral from 0 to infinity of f of x dx. But we already solved the integral from minus infinity to 0 of dx over 1 plus x squared, and we got pi over 2. So we only need to solve the improper integral from 0 to infinity of dx over 1 plus x squared. Now, for doing so, we need to take the limit when t goes to infinity of the integral from 0 to t of dx over 1 plus x squared. The integral is equal to arctangent of x, which we need to evaluate from 0 to t. If we do so, we get arctangent of t minus arctangent of 0, which we know is equal to 0. But remember that we need to take the limit when t goes to infinity. So we end up having the limit when t goes to infinity of arctangent of t, and this is equal to pi over 2. Thus, the integral from minus infinity to infinity of dx over 1 plus x squared is equal to pi over 2 plus pi over 2. Then it's equal to pi. Therefore, the area under the curve of the function f of x equal 1 over 1 plus x squared from minus infinity to infinity, it's equal to pi. I bet that you enjoyed this lesson. It was definitely really interesting. Now, if you want to keep practicing your knowledge, you can try to find the area under the curve of the following functions in the given interval. But in this particular case, you will require using improper integrals. So, well, guys, as usual, see you in the next lesson.